Last event, we had an amazing talk from Alex from Lightstep, who was talking about performance is not a number. And I guess as a continuation of his talk, Karthik today is going to present his amazing work on applying statistics to root cause analysis.
Hi, my name is Karthik Kumar, and I'm here to talk about applying statistics to root cause analysis. A few quick intros. I'm a software engineer, and I'm building root cause analysis tools at a company called Lightstep. At Lightstep, our mission is to build simple observability for deep systems, and we're focused on mainly distributed tracing. Our CEO and co-founder created Dapper, which is the distributed tracing tool used at Google. So the topics I want to cover today are two common problems with telemetry data, specifically around tracing. The first is around complexity and how we can maximize the insights we can get from tracing data while minimizing the complexity. We want to ensure that the monitoring software isn't more complex than the application itself. I also want to talk about how we can gather interesting data that we or the user cares about while minimizing the cost or the overhead of such high volume data. A PM shared this with me recently, and I think it's a good quote for this section. It says, "The function of good software is to make the complex appear to be simple." We want to build good tools to simplify the complexity of analyzing software performance. So I think it's pretty clear that as systems get more complex, traces and other sources of telemetry data become more complex. Traces can provide an end-to-end view of the request path, and analyzing them in aggregate can be really powerful in a complex multi-layered architecture like this one, where there's requests flowing from some mobile or web client through some microservices or some type of backend. Having tracing data can provide a good end-to-end view of the entire request. It can have rich contextual data, but root cause analysis can still be a little difficult and expensive. So that's what this talk is about. How can we maximize the insights and minimize complexity? And my hypothesis is that we can use statistics to make this possible. The first topic I want to talk about in this section is around distributions. At last year's Performance Summit, a coworker of mine talked about modeling performance as a shape and not a number. He advocated for using histograms and not just averages or percentiles to measure performance. And the main reason was that using averages and quantiles like even P99 can hide the distinct behaviors in your application, and they aren't helpful for understanding complex systems that have varied behaviors. The other benefit to modeling this as distributions is that we can visually compare changes in performance, which are harder to do when it's a single number you're looking at. I wanted to motivate this example by showing a few common behaviors with latency distributions. So here's 3 common patterns that we see in software performance and how we can use histograms and distributions to model that behavior. So the first one shows a long tail latency. So there's a few large requests towards the right side of the histogram, which represents the slowest requests. The second example has some type of either cache hit or some error code path on the left side and some normal path on the right side, which results in this split bimodal distribution. The third request could be something around different classes of requests, some that are expensive, some that are cheaper, and this also just appears as a bimodal distribution. If you notice between the second and the third example, there's not much difference in the P95, so if that's the number that you cared about, you probably wouldn't even notice that there's a difference in the behavior of these two distributions. And it really shows the power of how we can model, how we can immediately get a sense of how the system is behaving. So then the other thing we can do with this is to compare distributions. And we can do so visually by just overlaying histograms from different time periods. In this example, if you notice the vertical lines over here, the P95s didn't actually change that much, but the blue line represents something that was happening before the deployment, and the yellow bars represent after deployment. But because of the bars that we see closer to 1 second, this probably indicates a regression and warrants a rollback. And we're able to immediately get this insight by just looking at a distribution, which is not possible by looking at P95. So that's all I wanted to say about distributions. My main topic here is around correlations and how we can apply some basic statistics to find associations between behaviors and different subpopulations. And the behaviors that we care about are mainly latency and errors, but this could also be something the user cared about that they're telling us. And the subpopulations are things like spans on tags or services and operations, basically things that are information or properties of your system. And we can actually automatically identify these subpopulations and surface the ones that have a sufficient correlation to a certain type of behavior. And our goal is also to present this in an understandable way. So I want to present this as what we did to explore this project, and my guess is that this can be applied to other similar problems that you may be dealing with at your company. This actually started as a hackathon project. We used something called the Pearson correlation coefficient to find a simple linear correlation between two variables, x and y. And it returns numbers between -1 and 1, so values close to -1 are negatively strongly correlated with between the two variables, and +1 is the opposite. And values close to 0 indicate things that have low correlation. I've written potentially binary up there because we're going to look at some examples where we encode the properties of traces as binary variables for things like the span has this tag or the span is in some window. And the images that I've picked show real valued variables, but the idea is pretty similar. It's just an implementation detail. So I wanted to next share a few examples of how this works in practice. So on the statistics side, we're correlating two x and y variables. The x variable is spans with a certain tag, some payments succeeded tag, and the y is some latency that we're seeing in the sample of data. And how this is presented to the user is like on the right side. There's a payment status succeeded tag that has a 0.72 correlation coefficient. And this indicates that there is some strong correlation between that tag and slowness in our data. And that's represented visually here with something similar that we saw earlier, which is overlaying histograms. So the black bars represent spans that have this tag, and the blue bars represent all the spans in the sample. And we can take this data and immediately understand that since there's a positive correlation, we should expect to see the black bars closer to the right side of the histogram, and that is what we see. But there are some examples of some occurrences of this tag on the faster side of the histogram also. Similarly, we can look at a negatively correlated example with latency. In this case, a spans with a certain tag like HTTP method get is negatively correlated with latency, and that appears as a negative correlation, -0.8 here, and we can show this to the user by highlighting the left side of the histogram, and the black bars represent faster spans have this tag. We can also correlate with errors, and in this example, there's a perfect correlation with errors in the sample. So this is a span with the 400 tag for HTTP status code. And this, we don't really look at this in the context of a histogram because we're looking at errors, but in this case, there was a perfect positive correlation with errors and this tag. We can also correlate with user-specified behavior. So far we've looked at correlating against latency or errors, but we can also look at behavior that the user is interested in. In this case, they can select a region of the histogram. It may not be the slow ones, but it may be something between 500 milliseconds and a second and a half. And they want to know what spans appear on this tag. So now the Y becomes spans inside the region that they have selected. And in this example, there was a span that had certain service and operation on the critical path that was contributing positively to latency. And it actually works. This is the best type of feedback, right, on Twitter. And we've seen our customers who use this feature to actually find issues in their software without having to sift through large numbers of traces. But there's definitely pros and cons to this approach. And But first I want to show you the actual math behind what's happening. The Pearson coefficient is pretty straightforward. It's basically computing a covariance of two variables, x and y, and it divides that by the product of their standard deviation. Because of that denominator, the unit of measurement doesn't actually affect the calculation, which is a big benefit here. We can correlate with two variables that are measured in different units, and it would still return a valid value. It's also simple to understand and implement, and it works well for most cases. When it doesn't work well is when the data set has a nonlinear association between the variables. And we'll look at some ways that we've dealt with that. And there's also the possibility of type 1 and type 2 errors, since the data set is a sample of the entire population. But our goal wasn't to be 100% confidence in the data, and that's why we exposed the correlation coefficient to the user. We want to show them a confidence score to guide them towards hypothesis validation. So I talked about how skewed data wouldn't work well with Pearson correlation coefficient. And so I have an example here of some highly skewed data set, and we can use two techniques that, to make this data more easier to interpret and use statistical analysis on. One is the simple log transformation, where we take each data point and take log base 10. And another is to rank the data points on a scale of 0 to 100, so basically find the percentile rank of each data point. And this kind of transformation can be helpful in making the data more interpretable and to help make it so it can allow inferences on highly skewed distributions. We've also looked at correlating on nonlinear data sets through some other algorithm. We use Spearmans to just experiment on computing correlations and finding a monotonic relationship between the rank of two variables. And it actually works well when there's a nonlinear distribution and it's more resistant to outliers, but actually our testing didn't show much difference in the difference between the results between the two algorithms, so we haven't actually implemented this, but I wanted to share this as something that might work for your use case. So with Spearmans, it looks at a distribution of data and it tries to find a correlation with any monotonically increasing function. So in this case, Spearmans returns 1, but Pearson doesn't return a perfect correlation here, even though it seems like as x increases, y also increases. We see similar results without outliers, so both if there's no real correlation in the data, both Spearman and Pearson return similar coefficients. But Spearman's does perform well when there are outliers. So Spearman's correlation shows data closer to that are grouped together and tries to find correlation and is less resistant to those points on the right. We can also correlate with more properties, since I've shared a few so far, like spans on a tag, tags on a span, or certain services and operations, but we can correlate against more complex things like correlation. Since a subpopulation that we're identifying is just some feature of a trace, we can correlate on certain call patterns like serial or scatter-gather. We can correlate on logs with spans, the existence of certain spans up and down the trace. So it's really like a platform to build other types of analysis as we think of them on. So a few takeaways from this section. We talked about how tracing data is noisy and complex, and using histograms to model performance is really helpful in understanding visually what's happening in your system. And we can use simple statistical analysis to expose patterns in your data. You can guide hypothesis validation, and we can optimize the process of finding the root cause by not having people sift through trace by trace, finding what tag appears on which trace and whether that's correlated with anything manually. So I hope I've convinced you now that you can do some cool analysis with traces, and you might be wondering at what cost. And that's the next topic I want to talk about, data quantity. We obviously have a lot of trace data, and as our systems get more complex, traces get more complex. So we want to figure out what is the best data to capture. And so the topics here I want to cover are around bias and sampling. So the first question to ask is, what data does the user even care about? So we have a fire hose of traces coming in, and we want to identify the traces that are relevant to the user. And so our goal should be to focus our sampling budget on the interesting traces. So we define anything that the user cares about as interesting, and these could be real-time queries that they're running currently, or queries they've saved in the past and said, this is something I want to track the performance or behavior of. But we also do another technique. The first, looking at just the items the user told us to care about, isn't actually sufficient. We need something that gets a constant source of data for each service that they've instrumented. So we introduced the idea of using ingress operations to identify the entry point of the service and gather traces and other statistics for those ingress operations. And you might be wondering why we look at ingress operations. Well, that's usually what's used to report SLAs. So those are the operations that people care about for their service. And we can detect what an ingress operation is by looking at service boundaries and explicit tags that the user can set, saying this is an ingress operation. I also want to motivate why we want to bias the data. Bias usually sounds like a negative term, but in this case, we want to be guiding users to the root causes. And we've already shown that it's possible to automatically identify the subpopulations that might be interesting to them. So our goal with sampling is to capture enough traces that exhibit as many different interesting subpopulations as possible. So if we have a bunch of post-sample data that just looks like normal behavior, this isn't useful to the user. We want to bias our sampling towards the traces that have abnormal behavior. A quick aside here, the tracing architecture at Lightstep looks something like this. It's pretty similar to other platforms and other systems, but we have a trace library that's attached to microservices, which are usually the most common source of data, but there's others. And that data gets sent to satellites, which are basically collectors, and our backend SAS does queries back and forth to the satellites for relevant data. And there's 3 levels of sampling that we can do at the library, trace library itself, the collector, and at the SAS, and I'm going to focus mainly on the SAS in this talk. So we talked about why we would want to bias sampling earlier, and the next natural question is how do we bias the sampling? So we want to bias towards error traces and traces across the latency region. Usually when you hear the word sampling, you might think about uniform sampling, which is to randomly pick a point that's somewhere along the distribution. But we want to bias towards capturing the tail behavior, and we want to make it so in a distribution that's skewed like this one, we want to equally likely pick a trace from at any point in this distribution. And we have a few requirements also at the SAS around sampling. So we have an input of some stream of traces of unknown length, and we want to output a representative sample. And we want to use that sample later to answer some questions about the original population. We don't know the questions we'll ask yet, but this could be any type of questions that, any type of features that we build that would want to build off of this data. We want to make efficient sampling decisions. We don't want to be spending too much time actually flipping the coin to decide whether or not to keep a trace. And we want to make sure this works in a distributed setting. So there's no centralized coordination between different sampling locations. We want to make sure each decision is made on a local basis. And we actually found a solution in academia. There's a paper from 2010 called BarOpt Sampling that introduces an online reservoir sampling scheme. So reservoir sampling is the technique where you keep a reservoir of representative items that's some number smaller than the entire population, and you use those items to later answer questions about the entire about the entire population, which is exactly what we want to do. We can define each input item and give it a certain weight, and this is we call it importance, and this is something we can define ourselves. So this is where we introduce the bias. We want to add more importance to things that have latency or errors or version changes or even any other product feature that we think of in the future. And BarOpt ensures that there's a cap on the items with the highest weights. It also produces an adjusted weight that's different from the input weight for each sampled item. So this basically answers the question, how many other traces like this one were present in the population? And BarOpt meets our requirements. It minimizes the average variance of over the subsets. And we care about subsets here. This might not be intuitive, but we care about the subsets because subset sum weights can be used to answer the quantile queries that we care about, like what percentile does this trace belong to in the population. It makes sampling decisions very efficiently in O of log k time, where k is the number of items we care about keeping. And it works in a distributed setting. So I wanted to present how this works in a visual way. So we have a bunch of traces being input into our SAS, and these are traces for ingress operations. And we assign some importance to bias towards the interesting traces. And again, interesting here, it could be entire latency region covering errors from higher traffic satellites and so on. Those traces go into BarOpt, and BarOpt samples some k number of those items. and it guarantees that it will minimize the average variance of any arbitrary subsets that we want to draw from that data. And it does so in n times log k time. And we can take those traces output from BarOpt and store them and analyze them at some point later. And we can take subsets of those traces and use the adjusted weights to calculate some quantile measurements. So in this case, this adjusted weight of 33 in this first example means that there were 33 other traces that were similar to this one. And we can use those numbers to go back to calculating accurate percentiles of the whole population. There's a letter K here that is how many items we want to sample. And productionizing this means that we can decide how many traces to actually sample. I'm not going to go into too much detail about this, but K just indicates how big do we want our reservoir to be. How much money do we want to spend on CPU, memory, network, and storage? And the way we've solved this is to look at a rolling window of recent behaviors that we're getting from this population of traces for this ingress operation. So when a certain operation sees a spike in latency or errors or throughput, then we increase our K to appropriately also fill up our reservoir with more traces. We increase the size of our reservoir based on the behavior we're seeing. So a few takeaways from this section. Tracing data is very data intensive, but it's not all worth analyzing. There's obviously noise in the data. And we have several opportunities to sample, and each one has different constraints and requirements. But we want to be on the SAS side, on the back end. We want to bias towards storing and analyzing the interesting traces. That's where we want to spend our budget on. And we should be flexible in defining what it means for a trace to be interesting. And so what I presented is a solution that worked for us, which was BarOpt sampling. So in summary, I talked about data complexity and minimizing the complexity of this data and maximizing the insights we can get through distributions and correlations. And I talked about tracing data quantity and minimizing the cost and the overhead of this data while maximizing the relevancy and keeping data that we consider to be interesting through biasing and sampling methods. And that's it. Any questions?
Thank you so much, Karthik. It was an amazing talk, as always, super informative. Looks like we currently don't have, so I'm gonna just go ahead and ask the one that I'm very much interested in. So most of this is with regards to monitoring distributed systems and microservices. I'm wondering if you have any experience with using this for observing performance of mobile applications.
Yeah, so you're right that this is targeted towards more server-side monitoring, but we have customers of Lightstep who use tracers on their mobile devices to send traces on what's happening between the mobile to backend communication, and they can use pretty much all of the tools I talked about to analyze that behavior. And I don't think we have anything specifically geared towards mobile, but the same idea should still be relevant.
I see, and I assume that you're using OpenTelemetry for instrumenting.
Yeah, yeah.
So that's why it should be more or less uniform.
Right.
And by the way, thank you for working on OpenTelemetry projects, being such an active contributor. I mean, like the Lightstep is contributing a lot, and I really hope to see the entire industry converging on the same standard. That would definitely simplify lives for everyone.
Yeah, that's definitely a big priority. But we have an entire team dedicated towards contributing to OpenTelemetry.
Yeah, that's absolutely awesome. Okay, let's see if there are any questions.
I see
So
one.
there is one. So as I understand this, BarOpt sampling helps in analyzing long tails. Is that correct?
So BarOpt sampling helps us decide which traces to keep. It doesn't help to do the analysis I talked about earlier. That's a separate process that happens after. Basically, BarOpt helps us take this huge stream of data coming from satellites and we can input like our bias on what we consider to be relevant for our later analysis. And BarOpt helps us do that in a way that minimizes the variance. So the BarOpt name comes from optimizing variance, and it provides us a way to take all this large number of traces and give it some importance that we decide, and then it tells us how many traces to consider as being part of the entire population. So then we store that, and at some later point, when a user here as a performance engineer is interested in analyzing performance, they can use the traces that we've assembled for that BarOpt decided were relevant to keep. So it's not necessarily analyzing long tails, it's in support of that, but it's more to condense down the amount of data that we need in order to do the same type of analysis I talked about.
Awesome, thank you. No more questions, looks like.
I see one in Slack.
Yep. Yeah, please go ahead. I guess I don't know.
Yeah, so the question was, you talk about tagging traces with features, example based on the presence of a given event. How long are these traces, and are they gathered with respect to triggers specific to the latency metric you're optimizing? Wondering how you'd go about engineering more complex features. Yeah, so the tagging of the features, we respect tags that appear on the span, so things like a deployment version or a host name or any type of tag that a developer considers important for their application. And these traces can be pretty long. They could get up to, I think, thousands of spans long and several minutes in duration. And they're gathered with a bias that we input. This is the topic of the BarOpt that I spoke about. And they're not necessarily gathered with a correlation that we plan to do. It's gathered with the intention of doing some type of analysis. And then later we can run the correlations engine to use the traces that we've gathered to pick out when a certain tag occurs with slowness. So the engineering more complex features comes in on the analysis side, where we can think of more ways to correlate behaviors with subpopulations and use the traces that we've already gathered. I hope I answered that, George. And Matt had a question. I didn't quite follow how BarOpt makes decisions without coordination. So the main point that I intended to convey with that was just that BarOpt doesn't need any type of centralized coordination. It's basically just a piece of code that we've written to say, given a trace, how valuable is this? That's the only input that we're giving it. And this doesn't need any type of coordination. It's mainly looking at aspects of the trace itself. So like a feature of the trace, like how long was it? Was it an error trace, and so on? So there's no like centralized coordinator that's managing this. It's made at a local. It's making these decisions locally to look at the properties of a trace and assign it some weight. And it takes a bunch of these in batches, and it's in streaming fashion. And when it outputs a number of how many traces to keep, we can use that number with our based on our constraints of how many traces we actually want to keep. So it's more that the only input we're giving it is just how much weight to give to this trace. So there's no need for any coordination. And Rico asked, I'm a big advocate of distribution-based diagnosis. Do you have a sense of how difficult or easy it was for people to get used to seeing these two-color distribution overlays? Do they find it natural? What do you do to report up to execs when there are many statistics described? Yeah, this is actually a big concern we have, or a big area of improvement. Distributions aren't inherently understandable. I think when developers look at charts, they immediately think of it as a time series. And the charts I showed in my presentation are actually on a log-log axis, which also is kind of confusing to users. The thing that we've tried to do is to like simplify what is actually being presented and not overwhelming the user with numbers that may or may not be relevant when you're just communicating a behavior. And the correlation coefficient actually was also confusing to users. So we went to a different way of showing like a range of good to bad, as in like a yellow, green, yellow, red. So these are some ways we've tried to simplify this. And the overlays themselves have also been a little confusing, especially since some of them are lines and some of them are bars. So it's an active area of development, I would say. We haven't definitely figured it out, but I think that it's more of like a UX challenge at this point. Since we already have the data, it's about how we can present it in the way that makes the most sense. It's definitely a challenge. I see one in Blue Jeans. Can you talk about the different factors contributing to bias and what makes traces interesting? So I mentioned this a little bit. The things we consider to make a trace interesting are we basically bucket the trace into certain some fixed size buckets of a histogram, and things that appear towards the right side of the histogram, things that are slower, we give it more importance. Things that are errors, we give it certain importance, and things that are coming from high traffic satellites, we give it more importance. And this is another area that we're iterating on. We recently added the ability to monitor deployments. So we gave things that have certain version markers, or when we detect a change in version markers, we give that more importance. So this is like where we can inject any kind of business intelligence, business knowledge that we gained from looking at customer data and any features that we might want to build. And that's what we can use to decide what is interesting and what we want to keep.
Awesome. Thank you so much, Karthik. It was super informative. I think everyone thoroughly enjoyed your presentation.